the intermediate value theorem basically says if you have two x values in an interval that's continuous, has to be continuous, and you plug in the two x values, so they have f of a and f of b. Let's say f of a is 5, and when I plug in b, I get 11. Okay? There's got to be some number in here that when you plug it in, you're going to get 6. Does that make sense? Because every number between 5 and 11 is going to get hit somewhere in between these, yes? Okay. So, how we're going to actually do this is what if f of a is a negative number, whatever it happens to be, and f of b is a positive number? What number did you have to go past? 0. So we are going to do it to figure out if you have a 0 in certain intervals. Okay? So that's what the intermediate value theorem is. There is some number c that when you plug it in, you're going to get a 0. So you're looking for a sign change in the y values of a continuous function. All right? So, let's try one. Let's ignore the fact that this is written on already. I did teach this yesterday, though, so that's why. All right. So the first function we are going to plug in the interval they gave you is a 2 and a 3. So we're going to plug a 2 in. Everybody's doing this, I'm sure, on their calculators. So 2 to the 5th minus 9 times 2 squared minus 15. So you get negative 19. And if you plug in 3, you get 147. So I got a positive and a negative. So there's a 0 in there. Yes? Right? Which is the 0 closer to, the 2 or the 3? 2, right? So if I wanted to get closer and figure out a smaller interval, let's say f of 2.5 would be right in the middle, so it's going to be smaller than 2.5. Let's try f of 3. Not 3. 2.3. So plug 2.3 in. And this is if we were going to do all of this by hand, and we're going to show you a calculator too, but what if I'm in college and they don't let me use my big boy calculator? Because I'll tell you now, my son in calc was not able to do it. Yes, ma'am? Okay, so we said f of 2 is negative 19. F of 3 is 147. So negative 19 is closer to 0. So we are just saying, let's pick a number that's closer to 2 than 3. So I'm just throwing it out there. 2.3, okay? So 2.3 to the 5th minus 9 times 2.3 squared minus 15. Gives me 1.75. So now I know there's a 0 between 2 and 2.3 because I have a negative and a positive. Which one's closer to 0? The 2.3, right? Let's try 2.2. So you're just narrowing your window. 2.2 gives me negative 7.02. So now I know there's a 0 between 2.2 and 2.3, right? Does that make sense? Is it closer to 2.2 or 2.3? 2.3, because this is closer to 0. So you can kind of bounce back and forth and keep narrowing your window. So how to do this with your calculator? We are going to put the function in our graph, y equals. So if I go to y equals, I get x squared minus 9, or x to the fifth, sorry, minus 9x squared minus 15. And I'm going to go to my window. My original is 2, and I'm going by 1s. So you hit second table, and let's look. You can see there's a sign change. So I know my zeros between 2 and 3. If you just hit your plus key, let's now change what we're going by 0.1 to the nearest tenth, and you'll see 2.2 and 2.3. See that? Let's change it to the nearest hundredth, which is what we're wanting to do. Now we have, there's no sign change. You got to arrow down. You're looking for the sign change in the y. Well, we already said it was between 2.2 and 2.3. You see it? Between 2.28 and 2.29. So you can narrow that and estimate it. And is it closer to 2.28 or 2.29? 2.28. So it'd be like 2.281 or 2 or 3. Okay? Does that make sense? All right. Not going to worry about doing the second one. Moving on. So local extrema, zeros of polynomial functions. So when you're looking at the degree of the polynomial, that tells you the maximum number of zeros the polynomial can have. So in that first example, my polynomial is a degree, what? 4, right? So it has at most 4 zeros. The number of times that graph will turn is at most 4 minus 1, which is 3. So the number of turning points is always n minus 1. Okay? Now, let's go ahead and factor this. It's a little different, but these things come up, so let's learn how to factor with a quartic. First things first, I never leave my leading term negative. Factor the negative out, because it's always easier to factor with a positive leading term. Okay? Now, although this is a quartic, it's a trinomial, and we are going to factor it like we would a quadratic. What would you multiply by to get x to the fourth? X squared times x squared. What multiplies to the 2 that adds to the negative 1? Negative 2, negative 1. So then we factored it. So if you have a quartic that's, a fourth power, then it goes to the second power, then it goes just to the constant, you can factor just like a quadratic. So when I set each of these guys equal to 0, when I take the square root here, how many answers do I get? 2, plus or minus the square root of 2. When I take x squared minus 1 equals 0, I get x squared equals 1. When I take the square root, I get plus or minus 1. So we have 4 zeros. How many turning points would I have? 3 turns. So if you think about this, let's put our zeros here. Negative square root of 2, negative 1, 1, square root of 2. Now let's put it all together from yesterday. This is a negative even degree. So what's my end behavior? What do I look like? Is it both up, both down, one up, one down? What's a negative even look like? Both down. It's like a negative quadratic, right? So my end behavior is low and low. And these are just, doing this. Does that make sense? That's how you kind of graph it. How many times did I turn around? How many maxes and mins do I have? 3. Okay? So you can't have the same number of max and mins as you do the number of zeros. So you had to return 1 less. Okay? All right. This second one, these are all challenge problems, by the way. We could graph these and find these answers, but we're not going to do it because we're better than that, right? We don't need that calculator. This is a hard one. And again, because we are so good, we're going to do this. This is a 4 term, and we would factor it by grouping. You can't group it in the order that it is. It will not work. But you can move things around. So I'm going to group it like this. X cubed minus 1 and negative 3x squared plus 3x. Now this is going to call upon you to remember things that you might want to forget. All right? Does anyone remember how to factor difference of cubes? No one?
X minus 1
X. Well, you would think, but no. It's going to be x minus 1, and then this guy is x squared plus x plus 1. Kind of remember that? Mm-hmm. Yeah, it's okay. You won't ever actually do this, I don't think. Let's hope not. Over here, we're going to factor out a negative 3, and you would have negative 3x, and you'd have x minus 1. So, we have x minus 1 as a common factor. And we have these guys as a, what's left over. All right. Can you factor that quadratic? Factors of 1 that add to 2, or negative 2. Yeah. Oh, what's this look like? They're all three the same, aren't they? Do you guys remember expanding binomials last year with Pascal's triangle? Do you see the 1, the 3, the 3, the 1? And they alternated in signs and the exponents decrease? I didn't see it either. Guys, it's okay. So, I like this example because how many real zeros are you going to get? When you set this equal to 0, how many answers am I going to get? 1. Well, I get x equals 1, right? How many times does that actually occur? 3. So they call that a multiplicity. It's a repeated root, and that's what we're going to talk about in the next slide. It's a repeated root. So we have 1, 0. How many turn points do I have then? I have 1, 0. No turning points. Right? So we have 1, 0 is 0 turns. Think about this as a parent function. It's a cubic function, and how did it shift? 1 to the right? Do we have any turns with the basic cubic function? No. We have an inflection point. Okay, so there's not going to be turns there. Okay. Multiplicities are when you have a repeated root. So when you have it factored like this, this exponent tells you how many times it occurs. That's the multiplicity. If you don't have an exponent, if it's just an exponent of 1, then it's a simple root. Okay? So if you have that exponent when it is factored form, so I'm just going to throw one out here, and we're going to kind of put everything together. All right. So how many different factors do you have? Different distinct factors. We have this guy. We have 1 factor, 2 factors, 3 factors. So I can get 3 different zeros. So the first guy, 3x equals 0. So x equals 0. How many times does that occur? Once. So it's a simple root. You can say multiplicity of 1, even though it's not a multiple, just keep track of it. X minus 1 equals 0, so x equals 1. How many times does that occur? 2, that's the multiplicity. X plus 5 equals 0, so x equals negative 5, and that's a multiplicity of 5. If you add all the multiplicities together, that's your degree. So this guy is a degree. 1 plus 2 plus 5 is 8. Okay? So let's see what we can do with that. Let's go crazy. Here's my x-axis. We have negative 5, 0, and 1. You can put your y-axis in there if you'd like. That's fine. Oh, that would be on 0 maybe. Okay? What's the end behavior of an even degree that has a negative leading term? What's it look like? Even. Down. Okay? So that means if I want to graph it, I have to start low, come up, do some things, and end down, right? Now, here's what's cool. A simple root just crosses the axis. If it's a even multiplicity, it's going to go up, bounce off the axis, and pop right back down, or back up. It touches the axis and bounces. If it's an odd multiplicity, whether it's a 3, a 5, a 7, 23, it hits the graph at an inflection point. It does that little jog like the cubic does. Okay? So if I'm going to graph this, my negative 5 is going to come up and jog it like the cubic does. So it's going to come up. It's going to hit like that. It comes back down. The 0 is a simple... Do that again. Jog. 0 is a simple root, so it's just going to cross. And then 1 is a double, so it's going to pop and fall back down like that. So the multiplicities allow you to kind of see how the graph's going to go. Now, I'm not concerned if you get this max to where it needs to actually be, or this min. We want to be able to hit the graph, the x-axis, like it's supposed to. So, does that make sense? So one more little thing we have to be able to graph more accurately. And we're not using those stinking calculators, right? It's all here, guys. Oh, yeah. Okay, here we go. This is what we just talked about, the multiplicity. So let's look at this graph. All right, is that a simple root, a even root, or an odd multiplicity root? Simple. Odd. Even. So if I'm looking at this, the least it could be, the least this could be is a double root, right? The least this guy can be is a triple, and the least this guy can be is a 1. So if I add those up, the least this could be is a degree 5. Notice it only has 1, 2, 3 turning points because of this jog. So the number of turning points has to be less than the number of zeros, but it doesn't guarantee that it's 1 less than the actual number of zeros. It's 1, 2, 3 zeros, and we have 3. Okay? So multiplicities count when you count how many total zeros it has, but it only has 3 distinct, we use that word distinct, zeros. Okay? It could be 5.
Oh, okay.
But I said at least, the least it could be, okay? Has to be at least a 3. All right? Okay. So we are going to just buzz through this and do a quick sketch, see what we can do. How many zeros do we have? 1, 2, 3. What about multiplicities? Are they all simple? All right, so we have x equals 1, x equals, and all simple, right? So if I were to graph this, -2, 1, 3. What degree do we have? How many roots do we have? 3, so it's a cubic. Is it a positive leading term? Out front, is there no negative? No, it's positive. So we have an end behavior that looks like this. So it has to start low and it ends high. So we're going to start low and it just kind of crosses, nice and simple. It's high. Okay? And we're just doing quick sketches here. We're not getting real detailed. We're going to do detailed next. We have, again, there's 3 different zeros here. The first one is x equals what? If I set this guy equal to 0, what would I get? 0, what's its multiplicity? 3. Next root is x equals 1, multiplicity of 1, so there's really not a multiplicity. And the next one is and that multiplicity is 2. What's our degree? 6? Is it positive or negative? You're looking at the front. If you don't see a negative out front, then it's positive. So what's the end behavior? They're both going up, right? So we are starting at the high and going to end high. So when I hit -5, am I going to cross, bounce, or jog? -5. Cross, bounce, or jog? Bounce. So we're going to come down. We're going to bounce off of -5. 0, we're going to cross, bounce, or jog? Jog. So it's going to have to hit like a little thing. And 1, we're going to turn around and cross. So when you're looking, when you go to graph, is it a bounce, a jog, or just a simple cross? Okay? It kind of flattens out here. I didn't draw a very nice one, but it kind of flattens out. Okay? Okay, last one. And then we'll get to some actual graphing here. What's our first 0? 3, multiplicity of 2. Next one is -1, multiplicity of 3. What's our degree? 5. Is it a positive or negative? Positive. So where are we going to start? Is it start low and ends high, right? So our first 0 is -1. Is that a bounce, a jog, or a cross? When I say jog, I mean inflection point. So the bounce, is it an inflection point or is it just a simple cross? This guy. Jog. And this guy's going to be a bounce. So we're going to jog and bounce. Okay? Make sense? So you need to know if it's a bounce, a jog, or a cross. Your end behavior, huge. We're going to talk about y-intercepts. You could do the sign chart, which we'll do. Okay. Let's go through this. This would be like a quiz or test question. Determine the end behavior. This is in general form. It is not factors. So you're not going to be adding exponents. You're just going to say, what is my biggest exponent? So the degree is a 3. And is it positive or negative? Positive. So my end behavior should look something like this, right? So end behavior, if we're going to write an answer, we would write it in limit notation. So the end behavior of p of x to the negative is going to be negative. The end behavior of p of x as x approaches positive infinity is positive infinity. But I would always, let's do a little sketch so you know what you're doing. Find the real zeros and the multiplicities. So we have to factor. And I'm telling you guys, if you cannot factor, you need to practice. Okay? So if I factor it, I get x minus 3, x plus 2. So what kind of roots do we have? Are there any multiplicities, or they're all simple? They're all simple. And what are they? X equals 0, 3, negative 2. So I can actually put those on my graph. All right. What's the y-intercept? 0, right? If you look at the general form, you plug zeros in, whatever, the y-intercept 0. Guys, you can't have an x-intercept of 0 and not have a y-intercept of 0. You already have that point 0, 0. Using the test method, so we have this factored. Let's clone this little guy, bring him down here. Okay. We really don't need, we're going to have to need to do this on the test, but we can graph without doing this. If I put negative 3 in here, I would have a negative, and a negative. Is that a positive or negative section? 3 negative. Negative. If I put in negative 1, I would have a negative here, but a positive here, so that would make it a positive section. If I put in 2, I would have positive, negative, positive, so that would make a negative. And if I put in, I don't know, 4, I'm going to get 3 positives. These are all simple roots, so that sign chart should alternate. They're all simple roots, so it should alternate, okay? But we already know from our end behavior that we're going to start low in the negatives and end high in the positives. You see the sign chart, we're starting negative and we end positive. We knew that already from our thing. All right. So let's go to graph this. They're all simple, so we're just going to sketch. So by our sign chart, you go negative, then positive, then negative, then positive, and you can see that. And again, we're not worrying about where the maxes and mins are right now. We're just sketching it. Make sense? All right, let's do one more graphing one, and then we will get to the application problem, and then we'll be done. Skip. Let's do this one. It's already factored for us. All right. So let's get our zeros first. X equals 1 multiplicity of 2. X equals multiplicity of 1. X equals 4. And he's simple also. So our degree is 4. Okay, so if it's in factored form, you can just add the outside exponents or get all your zeros first and add the multiplicities. What's our end behavior? Think about it. We have a positive, even function. So the end behavior, positive. Right? Think of the positive parabola. So the limit as x approaches negative infinity. You know what? Don't even worry about writing it. We're just going to graph it. So just know that it goes up and up, right? What's the y-intercept? The y-intercept is not 0 here. You're going to plug 0 in for the x. So it's going to be negative 1 squared times 2 times negative 4. So you're going to write your function without an x. All the x's went away. What does that equal? negative 8. Remember, we're multiplying. Okay, so we're going to graph x equals 1, x equals negative 2, x equals 4, and my y-intercept's negative 8. So we want to make sure we hit that negative 8. And we are starting up, and we're going to end up. Negative 2, is it a cross, a bounce, or a jog at negative 2? Negative 2. Cross. What about 1? Bounce. What about 4? Cross. So we're going to cross, we're going to bounce, and we're going to cross. Does that make sense? You got to know where your bounces are, where your simple crosses are, and where your jogs are. We good? I love multiplicities. Last slide. This was the bonus on the test, a question like this. All right, so we have a box that's 7 by 20. And we are going to create, or I'm sorry, a piece of cardboard. We're going to create a box by cutting out corners. And that kind of, we fold along the dotted lines and we have a box. So I don't know how much I'm cutting out, so we're going to make those X's. Same amount. We got to cut out squares. So when I fold this guy up, what's the actual length going to be here? I was at 20, but I took away an X and an X, so that would be, yeah, 20 minus 2X. And what is my actual width? It was 7, but I took an X and an X. And what is the height? How much am I folding up here? Just X. So that's your volume. Length times width times height. And then we're going to graph it. Before we put this in our calculator, we're just going to leave it in that ugly factored form. What would the domain be? Would it be all rows? Can you have a negative height? No. Okay? So it's got to be positive. Because you can't be 0. If it's 0, it's still a flat shape. Yes? How much can you cut off and still fold something up? This side's only 7. So you can't cut more than 3.5. If you cut 3.5, you cut the piece in half and you can't do anything with it. So it's got to be less than 3.5. So a reasonable domain would be like maybe 0 to 3. Okay, so when you go to graph this, which we'll calculate that. And you can graph it in factored form. Calculator's cool that way. I'm going to go to my window, and I'm going to go 0 to 4, just so my window's nice and wide. My domain really less than 3.5 is what it should be, but we're not going to go halves. The max, I just put 200. It doesn't really matter what the max is. You can estimate a max by putting in about half your domain or whatever. And we're going to go to graph it. So this is what it looks like. And we want to find our max volume. So we're going to go to second calc and max. And this is not a cube or a quadratic, guys, so you can't do the opposite of b over 2a. This is not that type of thing. Left bound, make it 0. Make your right bound 4. You want the max in that window. So the max is about 102.2 units squared. So this is the max. This is the amount that you're going to cut off. That's how much your square is going to be on either end. Okay? All right. So you have the rest of the time to work on your